Want to dig a hole all the way to the other side of the world? What an adventure! But before shoveling, talk to a geologist. Geologists know a lot about the inside of Earth and can help explain some of the amazing things you'll discover on the way down. Earth is made of layers. A thin coat of soil and water sit like makeup on the top layer, which we call the crust. You can dig down through soil only a short distance, perhaps less than half the length of a soccer field, before hitting the crust, which is a shell of rock surrounding the entire planet. Like a slightly damaged eggshell, the crust is cracked. It's in about 20 pieces, which we call plates. The plates come in two varieties, ocean plates and continental plates. Ocean plates are about 5 miles or 8 kilometers thick. Continental plates are many times thicker, but the rock is lighter in weight. Where ocean and continental plates overlap, continental plates usually ride on top, like oil on water. Going through Earth's rock crust is tough work. The world's best miners have been able to go down only about 2 miles or 3 kilometers. Toward the bottom of these mines, a surprising thing happens. The crust gets warm. In fact, the mines need air conditioning. Deeper inside Earth, temperatures climb thousands of degrees. On the surface, we don't feel this heat because the crust protects us from it. Why is it so hot inside Earth? Geologists list two main reasons. First, Earth formed long ago through a series of fiery collisions of tiny hot planets. Some of that early heat still remains. Second, new heat is created inside Earth through a process called radioactive decay. Together, radioactive decay and early heat make the inside of the Earth up to 20 times hotter than the hottest kitchen oven. Just below the crust, about 30 miles or 45 kilometers down, the temperature is high enough to melt rock slightly, to make it soft and gooey. Geologists call this area with softened rocks the asthenosphere. A means without, sthenos means strength. The asthenosphere has rock without strength because it's weakened by heat. The asthenosphere belongs to a layer of Earth called the upper mantle. Below the asthenosphere, the upper mantle gradually hardens into solid rock. The hard portion of the upper mantle and the stiff crust above are held together like a jelly sandwich by the gooey rock of the asthenosphere in between. Maybe by now you've given up plans to get a shovel. Fortunately, curious geologists have figured out what's down there without digging. One tool they've used a lot instead of a shovel is the seismograph, which records the energy waves of earthquakes. Seismographs reveal that right below the upper mantle lies another layer of rock, the lower mantle. The lower mantle carries earthquake shock waves in a different way than the upper mantle, and this shows up on seismographs. An earthquake here gives different kinds of readings to seismographs here and here. The difference between upper mantle and lower mantle rock is mostly caused by one thing: pressure. The weight of the crust and upper mantle presses down on the lower mantle. Gravity pulls everything to Earth's center. Below the line dividing the upper and lower mantles, a sudden change takes place. Like water changing to ice because of cold, lower mantle rock changes form because of pressure. The lower mantle goes deep into Earth, then meets the core. The core differs from the mantle because it is metal, not rock. The metal, especially iron, sank here while the Earth was still new and soft because metal is heavier than rock. Like the mantle, the core is divided into two layers, inner and outer cores. The outer core is melted. The liquid metal is perhaps as thin as water and circulates or moves around the inner core. This circulation creates Earth's magnetic field, the force that makes a compass work. So the magnetic field people have used for centuries to explore the world comes from a part of the planet we will never visit. The inner core is also metal, but it is solid. As in the lower mantle, extreme pressure changes the form of the core's material. The pressure pressing in on the inner core is perhaps about the same as the pressure pressing out around an exploding atom bomb. The inner core's temperature nearly equals the surface of the sun.